Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to this course on gas turbines and jet engines. So, today is lecture 18, which is the third lecture of this week 4. Okay. So, we had already started discussing real gas turbines and what are the deviations from the ideal cycles. So, today we are going to cover a very important topic which is known as polytropic efficiency. Okay. So, polytropic efficiency is a type of efficiency which is defined for compressors and turbines. Today we will discuss what is polytropic efficiency for compressors, and in the next class we will define what is polytropic efficiency of turbines. Okay. So, the concept which will be covered today is what is polytropic efficiency, what is the significance of polytropic efficiency, why it is necessary basically, and then how to use the polytropic efficiency of compressor. Okay, so, this is the second deviation that we are considering after kinetic energy. So, we have started in the previous class discussing the effect of irreversibility. So, irreversibility we know that it is because of frictional losses, the compression and expansion processes become non-isentropic. So, we have already quantified it using isentropic efficiency, and today we will be quantifying it using polytropic efficiency also. Okay, we will define what is polytropic efficiency and use that. So, we have seen that the actual processes due to this irreversibility deviate from the ideal process and go like this from 0 1 to 0 2, and the turbine process expansion process will go from like this from 0 3 to 0 4. Okay. And the net effect was that the compressor work input was increased while the turbine work output was decreased. Okay, so, now let us, and we had quantified that using the isentropic efficiency. Now, the question is why do we need another efficiency? We already have isentropic efficiency, then what is the requirement for defining another efficiency, and how is it different from this isentropic efficiency? Okay. So, what is polytropic efficiency? First, let us try to understand why is it needed. Okay. So, what happens in isentropic efficiency is that if I have a single stage or a small region or small part of the entire turbine expansion or compression process, compressor compression process, the isentropic efficiency for that part can be accurately defined, but using that isentropic efficiency for the entire process leads to inaccuracy. What is the reason for that? Let us try to understand that. Okay. Let us try to understand that, and then we will come back to the previous slide. Let us consider this diagram that I have shown, the hand drawn diagram on the right hand side. So, we have here a 3-stage process. So, compression going from 1 to let us say some value 1 dash or something, then another second compression process and third compression process. So, these are the intermediate pressures. Okay. This may be P1, P1 dash, P2 dash and P2. So, in this case, if the isentropic efficiency of a stage is defined as eta stage, by definition eta stage is equal to the isentropic work output from a stage or work input to a stage by the actual work input to this stage. Okay. Isentropic work input by the actual work input. So, isentropic work input is this work input, which is for the process isentropic process going from here to here. Actual work input is for this process, okay, going from let us use another color. Actual process is going from here to here. So, this is the actual work input. So, in terms of temperatures, by cancelling Cp we can write in terms of temperatures. Okay. So, now for all the processes together, the net effect or net change in temperature can be written as delta T stage summation over all the stages. So, this is equal to nothing but summation of delta T s stage by eta stage, where eta stage is the efficiency of each of the stages. So, this is the isentropic efficiency of each of the stages. Okay, we are assuming equal isentropic efficiency for all stages. Now, separately we can also see that the overall efficiency of the compressor, if I define the overall efficiency for the overall process, this can be written as this length delta T s, delta T s, the isentropic overall isentropic compression by this line going from 1 to 2, which is equal to the summation of delta T stage. Okay. So, from this 1 and 2, what we get is that eta C by eta stage eta C by eta stage, this is equal to del T s by summation del T s stage. So, the overall isentropic temperature change going from 1 to 2s and the sum of the individual isentropic temperature changes, let us say that going from here to here, then here to here and this. Now, as we can see in this constant pressure lines diverge towards increasing entropy, okay, or at higher temperature we have more gap between two constant pressure lines. So, the length of this line, for example, is higher as compared to the length of this line. Similarly, this is longer than this. So, this expression, in this expression delta T s stage, this is greater, summation of this is greater than delta T s. Okay, so, this is less than 1, which means that the overall compressor efficiency is actually less than the individual stage efficiency. Okay. So, the overall efficiency is less. So, if I use individual stage efficiency for doing calculations for the overall stage, means overall process, we will get inaccurate result, because it is changing with the length of the process. So, you can now think of it as if a process is consisting of a very large number of small stages. So, if for each stage the isentropic efficiency is known, the overall efficiency will be considerably different. So, now which means that we need some sort of parameter, efficiency parameter, which remain constant whatever is the pressure ratio, whatever is the length of the process. If we have a larger pressure ratio, then also it is same. If we have a smaller pressure ratio, then also it is same. So, like this. Okay. So, this is where the definition of polytropic efficiency comes into consideration. Okay. So, what is this polytropic efficiency? So, as we have discussed, overall isentropic efficiency changes with pressure ratio. Okay, depending on the length of the process, the overall isentropic efficiency changes. So, for overall cycle calculation, fixed values of isentropic efficiency may not be accurate. Okay, so, we will define polytropic efficiency. So, what is polytropic efficiency? If we verbally just define, it is the isentropic efficiency of a infinitesimal stage, elemental stage, okay, or a stage with infinitesimal pressure ratio in the within the process, such that it is constant throughout the process. Okay. So, again if I want to define, polytropic efficiency is the isentropic efficiency of an elemental stage, infinitesimal stage within the process itself, such that it is constant throughout the process. Let us try to understand this better by drawing a TS diagram and then trying to understand what is the significance of what we are saying in this definition. Okay. So, let us say that we have a process like this. Okay. So, two constant pressure lines P1 and P2, and then this is let us say 1 to 2s, and the actual process goes from 1 to 2. So, if I now take an infinitesimal process or infinitesimal pressure ratio within this 1 to 2 process, let us do that. Let us take an infinitesimal process. So, in this process, the isentropic change is equal to the small line that I am showing here. Okay. So, let us say that this is equal to TDS or sorry DTS, infinitesimal isentropic temperature change. We will use another color, this is becoming too complex, maybe. The actual temperature change, which is equal to this, let us call this as dt. Okay. So, the isentropic efficiency of this small temperature difference and for the small pressure ratio dP can be written as eta, or let us not use any subscript right now. Can be written as eta equal to dTs by dt for the compressor. Okay. dTs by dt. So, ideal temperature rise by actual temperature rise. So, because this is an infinitesimal stage, by definition this isentropic efficiency is what we call as the polytropic efficiency, or polytropic efficiency, which is denoted by putting a subscript infinity. Okay. For the compressor, this is equal to dTs by dt. Okay. This is the not the small t, capital T, of course. Okay. So, this is equal to dTs by dt. So, polytropic efficiency is the isentropic efficiency of this infinitesimal stage. So, what is seen is that this ratio remains constant throughout the process irrespective of the pressure ratio, and this only depends on the manufacturing conditions, but the tolerances that are used, the equipment quality which is used for manufacturing. So, these are only dependent on the manufacturing conditions. So, for turbines which are manufactured in the same place using the same method, the polytropic efficiencies will remain constant, and we can have as many stages as necessary, still the polytropic efficiency will remain constant. Okay. So, this is constant. So, now this should be clear, the definition should be clear that this is constant. So, the main advantage of using this is that instead of isentropic efficiency, which can change with the pressure ratio, we now have an efficiency which is independent of the pressure ratio. So, we can directly use this for any pressure ratio or for multiple stages without any loss of accuracy. Now, we can of course relate this to the isentropic efficiency and get a value for the isentropic efficiency, and we can then use that isentropic efficiency, but we will see that we will get different values of isentropic efficiency for different values of pressure ratio based on a given polytropic ratio. Okay. Now, let us try to relate this polytropic efficiency for a compressor. So, this is the polytropic efficiency for a compressor. For turbine also we will define similarly. We will try to relate this to known parameters. Okay. How is it related to known parameters? So, if I have a process again, going from 1 to 2, this is the ideal process 1 to 2s, actual process is going from 1 to 2. With polytropic efficiency eta infinity c. So, if we have a elemental stage again, we will consider one. Okay, so, this is the value of dt. I am drawing in an exaggerated manner, and this is dTs. Again remember, we are drawing in an exaggerated manner. So, this is dTs, sorry, and this is dt, actual temperature rise. So, polytropic efficiency by definition polytropic efficiency we have written as dTs by dt. Okay. Now, for this isentropic part, isentropic process, we know that T by P to the power gamma minus 1 by gamma is a constant, okay, for the isentropic process. So, we can write this as T is equal to some constant C, C1 let us say, multiplied by P to the power gamma minus 1 by gamma. Of course, we can write this constant from the ideal gas law also, but we do not need that. So, this now we can express as, so because this is for the isentropic process, the temperature variable here is Ts. Okay. So, log of this isentropic temperature change ln Ts is equal to ln C1 plus gamma minus 1 by gamma ln P. If I differentiate both the sides, differentiate this equation, we are left with dTs by T, okay, because the variable is still T, the temperature parameter which is changing is T, but along the line of Ts. So, when we have written Ts here, it means that we are considering the change of T along this line instead of along the actual line. So, in one case Ts denotes the change along the isentropic line and T denotes the change of temperature along the actual line, but both are temperatures. Okay, both variables are temperature. So, this we need to differentiate with respect to temperature only. This is equal to gamma minus 1 by gamma dP by P. Now, using the efficiency definition combining with equation 2 we get from 1 and 2 that eta infinity c dt by t, okay, replacing the value of dts from this expression 1, from this expression 1. So, this is equal to gamma minus 1 by gamma dp by p. Okay, now integrating between 1 and 2 we get eta infinity c ln T2 by T1 dt by T naught. Ln T2 by T1 is equal to gamma minus 1 by gamma ln P2 by P1, which gives us an expression for the polytropic efficiency in terms of the overall parameters, which is equal to ln P2 by P1 to the power gamma minus 1 by gamma by ln T2 by T1. So, this is the polytropic efficiency, or this is how the polytropic efficiency for a compression process can be calculated. Now, this expression is important because P1 and P2 and T1 and T2 are measurable quantities. Okay. The way we had defined initially the polytropic efficiency we cannot measure, but we know what is the inlet temperature and pressure for a process and exit temperature and pressure for a process. We can measure those values. So, from this we can directly get what is the value of the polytropic efficiency using this expression. Okay. So, it can be calculated from measured values. So, this is important and we will later see some calculations related to this. Then what is the relation of polytropic efficiency with the polytropic exponent? This is one thing we want to know. The other point that we want to know is relations between polytropic efficiency and isentropic efficiency. We have already defined what is the polytropic efficiency of the compressor. Now, we want to find out what is its relation with polytropic efficiency. Now, you will ask the question that what is polytropic exponent? We have not talked about this polytropic exponent till now. We have only talked about polytropic efficiency. So, what is this polytropic exponent? This is one question, and a related question that may have come to your mind previously also is that why this efficiency is called as polytropic efficiency? Why this term polytropic? Okay. So, for that again we have the, so let us say the same process going from 1 to 2. So, we have written previously, we had derived that. Let us write here eta infinity c dt by t eta infinity dt by t equal to gamma minus 1 by gamma dp by p. dp by p. Okay. And from here we can rearrange the terms and we can find by integration T2 by T1, or even from the log expression that we had derived directly you can find T2 by T1 equal to P2 by P1 to the power gamma minus 1 by gamma eta eta polytropic efficiency, basically eta infinity c. Okay. So, now this is as if we have a polytropic process with an exponent n or nc, okay, So, this is as if we have a polytropic process going from 1 to 2 with an exponent n c, not eta, okay, n c, such that n c is related to gamma so that this n c minus 1 by n c is equal to gamma minus 1 by gamma polytropic efficiency. Okay. N c minus 1 by n c is equal to gamma minus 1 by gamma polytropic efficiency. Okay. So, as if this is a process which is governed by a polytropic exponent n c, okay, where the value of n c can be derived in terms of the known value of gamma and the polytropic efficiency. Okay. So, this as a result this process is a polytropic process, and we know what is the value of polytropic exponent because we can find it from gamma and polytropic efficiency. Okay. So, this means that the process is described by P v to the power n c equal to constant, this process from 1 to 2. Okay. So, that is why this efficiency is defined as the polytropic efficiency, and now we also know what is the polytropic exponent for this process, what is the polytropic exponent and how to calculate that polytropic exponent. Okay. So, directly we can do calculations using this polytropic exponent to find the pressures instead of using isentropic efficiency. Now, we also want to know, okay, so we can even rewrite this or rearrange this little bit to write the efficiency in terms of the exponents. So, eta infinity c can be written as gamma minus 1 by gamma multiplied by n c by n c minus 1. Okay. So, this is the value or this is the relation between efficiency, polytropic efficiency and the exponents, both the exponents. So, the final point in today's class that we are going to discuss is relation between polytropic and isentropic efficiencies, okay, relation between polytropic and isentropic efficiency. So, it is good to know what is polytropic efficiency, we know what is its importance now, but in many cases it is easier to do calculations using isentropic efficiency, or if we want to relate to other calculations it may be easier using isentropic efficiency. So, in those cases we may want to find out what is the isentropic efficiency of the overall process if we know the polytropic efficiency. Okay. So, for this we again, so our process is always fixed going from 1 to 2, but now we will also draw the corresponding ideal process. Okay. So, let us say that this is the ideal process going from 1 to 2s and the actual process going from 1 to 2, okay, which is a polytropic process, not a straight line. So, isentropic efficiency in this case we had defined eta c, okay, not n c, eta c T 2s minus T 1 by T 2 minus T 1. This is the way we have defined, right. So, this we can now we will try to relate this in terms of this, we will try to find out what is the polytropic efficiency. Okay. So, this we can rewrite as or rearrange as eta c. We can take, we can divide both the numerator and denominator by T 1. So, we will have T 2s by T 1 minus 1 by T 2 by T 1 minus 1. Okay. So, this can be written as R c to the power, where R c is the pressure ratio of the compressor. We could have written R, but to specify that this is compressor, we are going to use R c to the power gamma minus 1 by gamma, because this process from 1 to 2s is a isentropic process, minus 1, and 1 to 2 is a polytropic process. Remember, for polytropic process we have T 2 by T 1 equal to P2 by P1 to the power gamma minus 1 by gamma eta infinity c. Okay. So, this will be RC to the power gamma minus 1 by gamma eta infinity c minus 1. Okay. So, this is the relation between the isentropic efficiency and the polytropic efficiency. So, if we know the polytropic efficiency, we can calculate the isentropic efficiency from this expression, and you can try to find out some values. So, let us say that if the polytropic efficiency is 0.9 and pressure ratio is 10, find the isentropic efficiency, and similarly if the pressure ratio becomes 20, find the isentropic efficiency. You can take some values of T1 and some value of T1 and try to do the calculation. So, whatever we have discussed till now, these are all valid also when we consider the stagnation temperature T01, T02, T03. So, in general we will define all this, or we will write all this in terms of stagnation temperature. So, the say isentropic, for example, if one example if I take isentropic efficiency, we will write as 202s minus T01 by T02 minus T01. Okay. Like this we will define in subsequent problems. So, to summarize the class, we have defined what is a polytropic efficiency. We have seen what is the importance of this polytropic efficiency, why is it needed, okay, what is different from the isentropic efficiency, why isentropic efficiency is not always sufficient. Okay. And then we have analyzed polytropic efficiency, we have found how is it related to a parameter called polytropic exponent, what is the significance of this polytropic exponent, okay, and how it is related to isentropic efficiency. So, with this we will end today's class. These are the references, and thank you.